there's an open source implementation on assembly, but before this, let's look at the sorry, this is not fragmented, it's checksum. So let's look at this checksum first. So this is IP checksum in assembly, and it's optimized by writing this function in assembly languages. And what it does is that, see, the IPv4 checksum is only 16-bit long, right? 16-bit long. But on most computers, it's a 32-bit long. 32-bit. Each word is 32 bits. So what you want to do is this. You do the summation in 32-bit words first. And then you, after you finish, say I do the checks, I add up this. Each of them are 32 bits, which is the width of the word on most computers. So I add up this, I add them up. If you have option, I add them up. And then the result is now in a 32-bit word. And then I do this. I have all the result here, which is 32-bit long, right? 32 bits long. The summation is here, and in the register. And now I copy into another register. I copy into another register. Say this is R1, R2, another register. And then I shift the register I shift this by 16-bit. So I shift the content. I shift the content to this by 16-bit. So this 16 bits now is here. And then I do what? I add up. See, I add up this along with this to this. So I'm adding up this and this to this. So essentially, I'm doing what? I'm folding. See, I got the result here, but this is 32-bit long, and my checksum field is only 16-bit, right? So I can't fit. So I need to shift, and then shift this, and then add up into this. So I'm doing, but I can't do in place shift. So I copy and then shift. So now I got this and this. So this is here. This is essentially here, right? Because I copy and then shift. Copy and shift. So I got this, and then add up together here. So I got what? 16-bit. So that's because we are taking advantage of the 32-bit words. But at the end, we got 32 bits, which is too long to fit into 16-bit checksum field. So I need to copy and then shift and then add. So I'm doing copy, shift, and add. And then add into this. And this is the result I want, the result I got here. So I put this into the checksum field. Is it clear? It's simple, but a little trick here. How about fragmentation reassembly? There's a limitation from the link layer, which is called MTU, maximum transfer unit. Maximum transfer unit. And if an IP packet is larger than MTU, it needs to be fragmented. So let me finish this. So the packet is too large to fit into the link layer because the link layer has a limit on MTU, maximum transfer unit. Then you need to fragment into smaller packets. Then you need to identify the fragment. That is done by having all the fragment will have the same identifier, the field in the IP header. And then you need to know the position of the fragment, and it's recorded in the fragmentation offset, which is 13 bit in units of 8 bytes. Again, in units of 8 bytes. And you need to know the end of a packet. Who is the end of the packet? And there's a more bit, the more bit. And the last fragment should have the more bit as 0. So you got this as an example. This is the original packet, which is too long, 3200 bytes in data. So what you want to do is that you fragment into 3 fragments. And here they all have the same identifier, so that you know the receiver will know they belong to the same. And they have more bits on the first 2 fragments, but the more bit will be 0 on the 3rd fragment. And they have offset. Here it's 0, but here it's 185, and then 370. But why it's 185 here? If the MTU is if the packet the MTU is in this case, in this example, the MTU is 1,500. 1,500. But the fragmentation offset needs to be in units of 8 bytes, right? So the largest number, which is a multiplicative of 8, but smaller than 1,500, will be what? Will be 1480. So that's the largest number. That is a multiplicative of 8, but smaller than 1,500. So that's 1480. So, and 1480, if you divide it by 8, it'll be this, 185. Divide 1480 by 8, you will get this. So that's the offset. And again, you take this and this. If you multiply, again, because these two are the same, so 185 multiplied by 2 will be 370. Okay, that's the way you do fragmentation.